Silicon, the second most abundant element on Earth's crust, has been the go-to material for making integrated circuits or microchips, primarily because of its characteristic to act like a semiconductor, ability to allow or stop the flow of electrical current under different conditions. These chips are carved out of silicon wafers. Today, at least a dozen of these chips work together inside your smartphone. Every single chip contains billions of components, a majority of which are transistors or microswitches that turn on and off to represent the state of 0 and 1 and create digital logic. The very first integrated circuit or microchip was created in 1958 and had just one transistor. The very first commercially available microprocessor chip, launched in 1971, had 2,300 transistors. Seeing this trend, the then pioneer chip manufacturing company Fairchild Semiconductor's co-founder Gordon Moore predicted that the number of components in a chip would double every 2 years. As the components in a chip increased exponentially, so did the chip's processing power. The prediction was so spot on that it became known as Moore's Law. This was only possible because engineers continuously reduced the size of chip components. Today, the smallest transistors measure just 2 to 3 nanometers, barely the size of a few atoms. However, as we approach the physical limit of these transistors, it is becoming increasingly difficult to shrink their size every 2 years. As a result, many are questioning whether Moore's Law is dead. Of course, this is not the first time people have asked this question. Some even joke that the number of people who believe Moore's Law is dead doubles every 2 years. But to answer the main question, one has to look closely at the components governing this law. A transistor is essentially a switch that controls the flow of current. When a small current is applied to the middle base terminal, it changes the region's conductivity state, allowing current to flow between the collector and emitter terminals. When no current is being applied to the base, the region stays non-conductive and no current flows between the terminals. This makes the transistor a switch. 1 represents the flow of current and 0 represents no current. When billions of these tiny switches are integrated into a microchip, their rapid sequential switching enables them to process vast amounts of information using binary logic. Gordon Moore foresaw the pace of progress. In 1965, he predicted that the number of components on a chip would double every year, and it did. A decade later, in 1975, he revised it to doubling of components every 2 years. Transistors went from a dozen to 100 to 1,000 to 1,000,000 to 1,000,000,000 and now even 1,000,000,000,000 in some advanced chips. Moore's Law became a benchmark for companies to assess their performance pace. Hence, the law became a self-fulfilling prophecy, leading companies to rush to release new powerful chips with more transistors. Of course, as the chip got more powerful, it also needed to draw less power per component and be cheaper. If a decade ago a chip with 10 million transistors costed $100 at 1 cent per transistor, today a chip with 10 billion transistors also costs $100. Similar to the pricing, the power consumption per transistor also needed to decrease exponentially. This made computing power cheaper and more accessible over time. At first, transistors were designed by hand, but to scale it down further, it needed more sophisticated tools. In the 1950s, engineers discovered that if they coated a semiconductor wafer with a photoresistive chemical, then shine a light through a geometric pattern and an upside-down microscopic lens, the pattern light that would emerge would be much smaller and would interact with the photoresistive chemical, making a pattern smaller than 1/10 of a centimeter. This process became known as photolithography. Over the years, the process for creating miniature transistors refined, but as transistors got smaller and smaller, the chip industry faced a limit with the wavelength of visible light itself. It needed to find a smaller light, so it moved from visible light to ultraviolet to now extreme ultraviolet light. Today, tiny transistors designed using photolithography machines are much smaller than a human cell. These highly sophisticated machines can create millions of transistor patterns on a single chip. Today, the extreme ultraviolet machines capable of making the most advanced chips are built by only one company in the world, ASML from the Netherlands. Each machine costs over $100 million and is made up of hundreds of thousands of components. Of course, manufacturing chips with these tools and machines also mean that the costs would rise for the companies. In fact, there's also Moore's second law that says the cost of a chip fabrication plant doubles every 4 years. With all these variables at play, it is not easy to determine if Moore's law is dead. NVIDIA CEO recently reiterated that Moore's law is finished, though Intel CEO had a different opinion. In the past few years, we have seen a slight plateau in the progress of Moore's law. Recently, the world's largest chip manufacturer, TSMC, began producing 2nm chips, a new benchmark for the industry. Interestingly, shrinking down transistors is not the only way to fit more of them in a chip. Several methods and intelligent design techniques have been used to fit more transistors on the same amount of surface area. In a way, Moore's law still holds true as the number of transistors is increasing at a similar pace, but it no longer translates to the same amount of performance improvements in the chips. Although with massive investment in the industry now pouring in thanks to AI, we could see a change in trend. Surely, at some point, we need to find other methods and techniques to keep up with the pace of not only this law, but also with the demands of the consumers. As you shrink transistors down to the atomic level, its behavior starts to get unpredictable. The electrons start to pass through the transistor's gate via a concept of quantum tunneling, because the transistors are no longer large enough to stop the flow of electrons. Perhaps the way out of this physical limit is to embrace it. Quantum computing is one frontier that has been hailed as the next big thing to take digital computing forward. At some point, we might encounter an impossible physical limit to shrink transistors, but for now, it would be a shame if we can't have computers with more processing power. What do you think about this law? Like and subscribe before sharing your thoughts in the comments.